let's now move on to part B of this problem. For part B, our turbine is only going to operate at 80% efficiency, or the shaft work is only going to be 80% of what the maximum shaft work would be, which is what we solved for in part A. All right, and so for part B, essentially, even though the efficiency is lower, the material balance and the energy balance equations are going to be almost the same as what we had in part A. And so for the material balance, it's actually exactly the same. M2 is equal to M1, which is still 4,500 kilograms per hour. For the energy balance, algebraically, it's the same. Our shaft work for part B is still going to be equal to minus M1 H1 hat H2. Maybe I'll call this one B. And so H1, the inlet stream, that's still the same. M1 is still the same. But for part B, our shaft work and this, our H2, are going to be different. To figure out the shaft work, it's fairly straightforward. We know that's only going to be 80% of the maximum shaft work, which is what we solved for in part A. And that turns out to be 501.7 kilowatts. Okay, and so now that we have the shaft work, really our only unknown is H2B. So if we solve for H2B, we figure out that it's 3020.8 kilojoules per kilogram. Okay? And so now that we have the enthalpy, in order to figure out the temperature, and eventually we're going to need to figure out the entropy of the outlet stream for part B, what we could do is sort of just kind of take the same steam table approach that we used in part A. All right, except this time we're going to start with the enthalpy rather than the entropy. And so what we're going to do is we're going to repeat our steam table approach. To find T2 and S2 hat. Okay? And so H2 is about 3,000 here. And so what we're going to do, since the pressure is still the same, it's still 1 megapascal, we're going to go to the P is equal to 1 megapascal superheated steam table value. All right, we're going to look for enthalpy values that are slightly above and slightly below the 3020 value. Okay? And so we see at 250 we're at an enthalpy of 2942, and at 300 we're at an enthalpy of 3051. So we're going to interpolate across the 250 and the 300 temperature values. Okay? So here we write down that H hat 250 is equal to 2942.6 kilojoule per kilogram. H300 is 3051.2 kilojoule per kilogram. And we interpolate. H2B minus H250 minus 250 degrees C. Our only unknown is T2 again. So if we solve for it, we get T2 is equal to 286.7 degrees Celsius. Okay? And so we see in this case, when we operate at lower efficiency, the steam that's leaving the turbine is at a higher temperature than if our turbine operated at maximum efficiency. Okay? And so not all of the energy that came in with the steam, not all of the possible energy that got extracted was removed. And so as a result, some of that energy still remains with the steam. And so that's why it's still at a slightly higher temperature. In any case, now that we have T2, we could go back to the steam tables and interpolate the entropy values in order to get the S2 value. Okay, and so we go to the steam tables. We just look at the entropy values for 250 and 300. We have them there. Let's now write them down. S250 is equal to 294246 kJ kgk. S300 is equal to 7.1229 kJ kgk. Let's interpolate. S250, 300 degrees C minus 250 degrees C is equal to S2 part B hat minus S250 divided by 300 minus 250. Our only unknown is this. So solve for S2 part B, and we get a entropy of 7.0677 kilojoules per kgk. And we see here our entropy is slightly closer to the 300 value than it is the 250 value, and that's because our temperature is closer to 300 than it is 250. In any case, now that we have the S2 value, we could go back and set up our entropy balance now. So ds dt is equal to m1 s1 hat minus m2 s2 part b hat, plus if we had any heats, they would go here, and then we also have sgen dot. Of course, even though the efficiency is lower, we're still adiabatic, so that's going to be equal to 0. We're still also operating at steady state. Okay, we also know that m2 is equal to m1 still, and so what we could do is we could rearrange this equation so that we get sgen is equal to m1 s1 hat minus s2 hat, or actually s2 hat minus s1 hat. And the reason these flipped is because since this is equal to 0, essentially I just moved all this stuff to the left hand side. Okay, and so now we have s2 minus s1. Alright, at this point all we need to do is plug in. So let's do that. .0677 minus 6.8803 kJ kgk, and we get that the entropy we generated is equal to 0.234 kilojoules per kilogram second. Oh, I forgot just to be complete, let me put the unit conversion in there. Okay. Alright, and so we see that when we operate at less than 100% efficiency, we generate some entropy in our system.